All right. So last time we did an introduction to assembly. I just wanted to do some review here, like a couple of questions. Give you a bunch of code, see if you can tell me what's going on here. So let's start just by saying, all right, what does LDI stand for? It's a opcode. It's a mnemonic for what instruction? Mm-hmm. And somebody else raise your hand. STS. Somebody besides Alex. Edwin, you were kind of down here, so. To what space? Store to some space. To storage space. That's not really what the mnemonic is, but what two kinds of space do we have in a processor, a microprocessor, or a microcontroller? Yes? Okay, which is what kind of technology? We talked about two kinds of memory technology. All right, SRAM is static RAM, but RAM, random access. And what's the other one that is not RAM? No, SRAM is also a type of RAM. ROM. RAM and ROM are the only two kinds of memory. Registers are just flip-flops and so forth, but RAM and ROM are the two big ones. So STS is for the RAM, meaning you can edit it. You can load and store. So, and which way does data flow in the AVR processor? Right to left. You know that yesterday or Thursday, whatever it was, I went back and I looked. When I said I must have said it 12 times, you know how many times I had said it? Twice. I felt like I said things that were close. I was like, data always flows towards the mnemonic, flows towards the thing, all these different ways, but never once did I say right to left. I only said it twice by the time I had said that. And then I sort of stopped counting because I did have, like, I had the little counter going. It was like, ding, ding, and it was like, I've only done it twice. This isn't. Anyway, so the question is, what's the contents of memory going to look like after this code is executed? By the way, it goes down and then back up to the top and down again. First off, somebody tell me what memory addresses are affected. We'll do one per person so that the pressure isn't too bad. Somebody raise a hand. 92 is a memory address that is affected. Somebody else. 93. I'm sensing a pattern. Somebody else. 94. What else? 95. Are there any other memory addresses that are affected now? Raise your hand if you think there is one and tell me. 85 is not a memory address that is affected. All right, so here's the trap you fell into. LDI has a particular syntax. It's register and then value, not address, value. So this says load into register 16 the number 85, not the value at a memory location. So STS says whatever is in R16, whatever that value is, put it into memory location 92. You can think of it as a very tall mailbox with a bunch of slots. Just like in the ECE office, you can find my name and put mail into it. 92 corresponds to just a location in memory. So any other memory locations that are affected? Yeah, 96. So we can look at the STS instructions. 92, 93, 94, 95, 96. Those have information that is stored into them. So if I've got 92 through 96, what is going to be in those? Let's start with what's in 92 at the end of this code. What's in location 92? Alex? 99 hex. Yeah, we take 99, we put it in R16, and then we take R16, put it in 92. 2 steps to get the number into memory location. When we talk about macros, next class maybe, you'll see that there's quicker ways to write it, although not quicker ways to execute it. And that's what this is. It's a group of LDI STS statements. So we're going to put 99 into location 92, 85 into location 93, 3F into location 94, 63 into 95, and 12 into 96. That's it. All right. And that's all those instructions do. They do very simple things. And if you break it down one instruction at a time, it's pretty easy to see what's going on. Try something else here. We've dealt with LDI instructions. We've dealt with an add instruction. What is the contents of memory location 120 after this has been executed? What numbers are we adding first off? We can see them in the immediate instructions. They're 5 and 2. What's 5 plus 2? 7. Raise your hand if 7 is stored in address 120. I got a couple takers. All right, how many people disagree with those couple takers? All right, in the blue shirt, what is stored in address 120? 9. I got to actually read it now. 5, 6, 7, 8, 9. Yeah, I agree. 9, because this first one is going to change the value in R20. R20 is going to become 7. R21 remains unchanged. So 7 plus 2 on this next line is 9. And finally, we store that number 9 into address 120. Okay. We'll skip those for now. So that was sort of the end of those slides on the end, just to keep you in mind of what's going on with these assembly instructions. So today we're moving into talking to the outside world. I/O ports in the AVR core. So the AVR core is just one, not hierarchy, not schematic, architecture. There we go. One architecture of many. We've got various architectures. ARM has, or rather, this is not ARM. This is an AVR core. ARM is a different core. We have Intel cores. We have AMD cores. Although sometimes they're based on other licensing technologies, so don't take that to the bank. I/O ports in the AVR processor. By the end of today, you're going to know how to do all this stuff. You're going to understand how to read. Well, you should. If you don't, office hours, tutoring center, etc. Understand how to read and write to physical I/O pins. I've got one of the 328p processors right here. Obviously, there's a bunch of metal pins on here. You're going to learn how to make those put voltages out. Okay, really just one voltage, high and low. Yes?
This is kind of random, but are these chips that we're using capable of pulse width modulation?
Yes. Okay. Check out the syllabus for the chapter entitled Pulse Width Modulation. Okay. It's on the back of the book, by the way. If you just look, there's a series of chapters. Pulse Width Modulation is one of them. You're going to be able to describe what's going on inside the chip. So leading to this piece of metal on the outside of this chip, there's a whole bunch of circuitry. You're going to understand what that is. You're going to be able to name the actual ports on this particular chip. This is the ATmega 328p. So you're going to be able to name all of the ports. You're going to know where the button and the LED are located on your development board and what port pins they connect to. You're going to know how to adjust just a single pin without adjusting any others. And you're going to be able to make decisions, simple decisions, based on I/O values. Okay. If you are looking for more information, if you look on the data sheet, there's section 14. I've got the PDF open here. It's all bookmarked. I/O ports is section 14 on the data sheet. And there's one thing that you kind of need to know. We've seen it a couple of times. This instruction called RJump is a way of not doing things in a linear fashion. So when it says RJump to location 1, it means that it's going to jump to location 1 wherever it is. It's just to keep things looking fine. All right. We won't have to worry about that too much. I have a whole chapter on jumps and branches. All right, so let's talk about pinouts for a second. Here is a Mega 32. It's a bigger processor. It's got a lot of pins. And there are some that are more vital than others. You obviously have to turn the thing on with power. So I've got VCC and ground there. You have to give it some kind of a metronome so that it knows how fast to run. In this case, it's a crystal oscillator, these two pins, Xtal 1 and 2. There's usually some kind of a circuit to make sure that we boot up in a known state. So there's a reset pin. This right here is a pull-up resistor and a capacitor so that we can't, so that we eliminate glitches and so forth. Basically, pulling this guy low will reset the processor. Everything else is an I/O port. On this chip, we've got very creatively named port A, port B, port C, and port D. And it's even wired nicely. A is up in the top right, B is top left, C is bottom right, D is bottom left. Now, everything you see in parentheses there is alternate pin functions. Because this is a microcontroller, sometimes you might want to use certain peripherals and sometimes you don't. So it's a trade-off. You can use those peripherals or you can use those pins as discrete I/O. And we'll talk about a bunch of this stuff eventually in the course. Okay? And I say everything else, there's a few more pins, specifically for the analog portion. We've got an analog ground, an analog VCC, and an analog reference. Everybody's okay with VCC being called power and G and D being called ground? All right, that's something you've seen before? Okay. Now, this is a 40-pin dip package. It's like 0.6 inches wide. There are others that you can use, and generally, it sort of follows along this kind of a thing. The more pins you have, the more ports you have, to the point where the ATmega 128P is 100 pins, and it's got ports A through L. Some of these chips have reduced pinouts in certain things. When I say a port, I mean a full 8 bits of pins, rather. So some of these have reduced. So for our case, the 28-pin dip that I've got right here, it only has port B, port D, and 7 bits of port C. So there is no C8, or C7 rather. It's got C0 through C6, and that's it. Let's just look at that for a second. Here is, from the data sheet, the two the two package formats we're using. Okay, on the right, you can see here is the 328P. It's this chip I'm holding right here in my hand. The rest of this is a breakout board, by the way. The chip is just this piece of plastic. I've colored it. It's not quite as nice as the ATmega 32, but you can still see port C is kind of together. Port D is on the left side. Port B is kind of all over the place. Okay, but that's where it is. The purple pins, those are your power and your analog pins. Right. Notice that there are 2 grounds, one for an analog ground and one for a digital ground. The TQFP package, it has one extra thing. If you look, there are 2 pins marked in red here. Those are 2 extra analog pins. Okay. Alex, you asked about PWM because you were thinking about an Arduino, weren't you? Yeah, this is the chip on the Arduino. Okay. Just, yeah, clarify that. So the TQFP package is actually 32 pins. It's got 2 more extra things. In class, we're going to be using a development board. This is the development board we're going to use. And there's 2 things I want to tell you right off the bat. There's a button on there, and there's an LED on there. You can use that LED to blink and just to show that something is happening. The board is kind of divided up into 2 spots. This little guy, that's actually the processor we're developing for. And it's a QFN package, so it follows this kind of a pinout. All this stuff up here, that's all so that you can debug nicely. All right. This is the bare minimum that you need. This is literally, that black piece is the chip. That orange guy is a resonator. It's got a little bit of a power supply built in there. Very bare minimum, a 7805, I think. And that's... Oh, it's got 2 LEDs on there. One is a power LED and one is an LED you can blink. That's it. That's all you really need. But this is a bunch of debug hardware so that you can go through and line-by-line debug as if you were in the simulator. Everything else is pinouts. If you purchase one of these from the DigiKey link, one of the other pieces that you're going to want to purchase is female headers. It comes without those. And rather than soldering in, we want to be able to use our hookup wire. So we can solder that in. And it comes with 2 footprints. One footprint is the Arduino footprint, which I find I loathe, specifically because of this gap right here. That's not a standard 0.1-inch gap, but the breakout board makes it nice and easy for us. Basically takes those and moves it, you can see. Over there, same pinout. Unlike the Arduino, we don't use things like digital 1, digital 2, digital 3. We actually have to deal with the names of the ports. BD0, BD1 through BD7. Here's B0, there's B5, C0 through C5, and so on and so forth. Okay? And it all runs off a USB port. So you plug this in, you got a full-featured development board. Okay. Questions so far? Yeah.
What did you say we needed? Email headers?
It's on that DigiKey link that I sent out. Okay, it's one of those things. Yeah, female headers. I think you need to get 2 40 pins, and then I'll cut them and solder on for you. So internally, there's a bunch of things that are happening. Specifically, every port has 3 registers that describe how the I/O is going to function. Those 3 registers all take on the form DDR something, port something, and pin something, depending on which port you're talking about. If we go back to all of these, we have ports A through L for the AVR cores. So if I am talking about port A, then I'm going to be talking about DDR-A, port A, and pin A. They're 8-bit registers that correspond to some pins on the device. It's bitmap, so that bit 7 controls a single pin, 0 controls a different pin. So you don't treat this as a 8-bit number. You treat this as 8 individual bits that happen to live in the same register. You can think of them as flags if that helps you. But each port has these 3 registers. Port A has DDR-A, port A, and pin A. Port B has DDR-B, port B, pin B. Now, these are in the special I/O section. I/O sections have a special set of assembly instructions to access them. Anybody remember what those 2 instructions are from last class? In and out. In and out are how you're going to be dealing with these until we learn some new instructions towards the end of class today. Okay, let's see, how quickly do I want to go here? Okay, so internally, there's a little bit of setup. Each pin that we talk about has a particular bit in those 3 registers. And the first thing I want to talk about is output versus input. You have to decide if the pin that you're going to be using is going to be sending out a 0 or 5 volts, or if it's just going to be reading. So here's how you do that. First off, the DDR register has nothing to do with dancing games. It stands for Data Direction Register. DDR stands for Data Direction Register. If the data direction register's bit, and so when I say DDR for now, I'm talking about a particular bit. You can set up each pin to be something different if you want. DDR equal to 0 means that it's an input pin. So if I put a 0 in DDR B7, that's an indicator that this physical pin, B7, is going to be an input. 0 is the same as an input. A 1 is an output. Now, if something is an output, then writing a 0 or a 1 to port B will output a 0 or a 1 on a pin. But a 0 or 1 on a pin is actually a voltage, so it's either ground or VCC. In our case, we're using 5-volt logic. So if you put a 1 into port B while it's an output, you'll get 5 volts on the pin if you measure it with a multimeter. If you put a 0, it'll be ground. So that's if it's an output. Port will control things when it's an output. I've got down here a little table. For now, let's just look at the yellow grouping. If the data direction register bit is a 1, if you set up a 0 on the port register, you'll output a 0. If you set a 1, you'll output a 1. If it's an input, things get a little bit more interesting. If you are set up as an input, you have 2 ways of looking at things. The first is a high impedance input, which is what most of you are familiar with, even though you may not be familiar with the term. When you dealt with logic gates and so forth, they were generally high impedance. They didn't draw much current. And so high impedance, another way of saying Z stated, no current will flow into the input. It will just read the voltage. If you put a 1 on the port register while it's an input, it configures it so that there's a pull-up resistor. Pull-up resistors are there for devices when you don't want it to be high impedance, specifically things like buttons. If I go back to that original setup here, this is an example of a pull-up resistor. Normally, when this button is unpressed, this reset pin has nowhere to go through the button. Current doesn't flow through the capacitor. So the only way that current can flow is this way, through that resistor. Now, reset is a high impedance input. Means no current flows. If there is no current flowing through that resistor, based on Ohm's law, V equals IR, V is the voltage drop across a resistor. R is the resistance. Let's call it 10K for now. 10K resistor. And the current is 0. What is the voltage drop across a resistor in that situation?
0.
Yeah, it's 0. Which sounds a little counterintuitive, right? But we have no current flowing, so there's no voltage drop. That doesn't mean there's no voltage. It means there's no voltage drop. So if I take 5 volts and drop 0 of it across this resistor, what's the voltage on the other side? Whoa. What's the voltage on the other side? 5 volts, which means this reset pin, which is active low, sees 5 volts. Everything is copacetic. We see a 5 volts. We're not resetting. Everything's good. That's a pull-up resistor. When I press the button, current now is going to be flowing through this because it's going right to ground. Now, in this case, I've got 5 volts, 10K resistor, but it's connected directly to ground. All of the current must be flowing to ground. If all the current is flowing, that means that the voltage drop across this resistor is 5 volts. So now, looking at this line, 5 volts minus 5 volts is 0. So we get a reset signal. So when you press it, this pin actually sees a 0. When you release it, the pin sees 5 volts. We have on all of these port pins internal pull-ups that we can actually turn on. So going back to this setup here, if we want, we can either be a high impedance input or we can activate an internal pull-up. Again, I'm going to show you the hardware in a second, but keep this in mind. Okay, if you're an input, you're either a high impedance input or a pull-up, or your input is pulled up. If you're an output, you're just outputting 0 or 5 volts. Okay, so this is just a reminder that the 328P has the same limitations I showed on this table. My goodness, I have a lot of things in this slide. We're here on the 28-pin version. We've got all of port B, all of port D, only 7 bits of port C. Okay, so what I've got here is 3 registers for port D, 3 for port C, and 3 for port B. And you'll notice that there's 1 pin in port C that's not assignable. All these say, by the way, is port D7, port D6, port D5, D4, D3, D2. It's a lot of verbiage to basically say each of these is individually controlled. All right, so here's our first test. Can we write a program that makes all of the pins of port A high, 5 volts, show 5 volts? In order to do that, this takes 2 steps. First, we have to set them all as outputs. If they're not outputs, we're not going to be setting them high. Then we actually have to physically tell the processor that we want to output 5 volts. Logically, what we need to do is set all of the pins of the data direction register to 1 and all of the bits of port A to be 1, in that order. Okay? Overall, it's not that hard. It's actually easier than some of the designs we've done before. First, I load up FF into a register. Why didn't I use R0 here? Did I just pick R20 out of the air? You can only use 16 to 31 for LDI. Any immediate mode instruction, only 16 to 31. That's my coffee not being drunk correctly. The second step is I use the out instruction. I have to use out in order to use those names. If I had tried to use, well, what's the alternative to talking to data space if I'm not going to use out? STS. STS cannot use these names, port A, DDRA, because those are designed to work without the instruction out. Okay? And in this case, since I'm loading the same value into both I/O locations, I only have to use register 20. I put R20 into port A and R20 into DDRA. Registers don't lose their value after you put them somewhere. They maintain their value. Okay? As another example, here's an example that will toggle all 8 bits forever. And this uses this instruction that I haven't talked about too much, We're just going to go over it first because it's the new thing. R jump to L1 just says, once you get to this instruction, execute this instruction next, because it says L1. So jump to L1, execute. So it's going to run this thing forever. It's an endless loop. So what does it do before the loop? Loads up FF and sends that into the data direction register for B. Alex.
I thought you said you have to set the DDR to 1 before you can put like set high before.
I did.
But in the previous slide, you did port A to FF and then DDR.
Okay. Valid observation. Let's go through what actually happened. So let's assume for a moment, you're right. I said that. In practice, this is running at 16 megahertz. So for 62 nanoseconds, it's in a bit of an off state. But here's what happens. If DDR is 0, right, because at here it's going to be 0, and the port pin is 1, what part of this grouping are we in? DDR is 0, port is 1. It's pulling up to 5 volts. So for a fraction of a second, we're going to be pulling up to 5 volts through a 10K resistor, and then we're going to be outputting a hard 5 volts. Sometimes that might really screw you up. Depends on what's on the other end of that pin. Okay, if you're trying to drive a motor, which you shouldn't, that could be a problem. Yes?
So on average, it's like good practice to set up a DDR before dealing with anything else?
That's how I do it. But as long as you're doing it one after another, literally happening 62 nanoseconds apart or less. Okay, so in this case, I do set up the DDR register first. And in this case, then I load up 5, send it to port B. Then I load up AA and send it to port B. 5 and AA are complements of one another. So let's see if I can do this. Here's, there's 5. I think if you're looking at, yeah, you're looking at 5. And hold on. There's A. So when I send it, what you'll see is they toggle every other bit. That was really complicated. So together, if you were to OR 5 and A, you'd get F. Okay, but if you take and you put out 5, then you put out A, what you're doing is the bits that were on are off, and the bits that were off are on. So it's a cute little back and forth blinky pattern. All it's doing, each little step, LDI then out, LDI then out, LDI then out, repeat. It's a fairly common code pattern that you'll see. Load into a register and then send out to an IO register. When we talk about macros next class, we're going to make this much easier to write. Okay, let's add on a few little things here. Oh, let's not add on because we haven't talked about call. To hell with that. Okay. All this does, it adds this line right here to a delay routine. We haven't talked about calls or delays yet, but we will. Just know that right now this is, well, this one's running at 16 megahertz, which means it's blinking on and off 16 million times a second. If you've got a chronograph, on your watch and you see it going, like even if just basic Timex kind of a stopwatch, can you really see the lowest digit of that, decimal digit? So it does seconds and milliseconds. Can you really see the milliseconds go by, or is it just kind of a blur? It's a blur. Maybe you can see like the tenths of seconds. You can maybe see go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and repeat over and over again. This is doing it 2 orders of magnitude, 3 orders of 4 orders of magnitude, many orders of magnitudes faster. So what you're actually going to see, you're not going to, here we go again. Yeah. You're not going to see it go this, and then this, then this. You're going to see it go so much so that it will end up looking like they are all half brightness, okay? Because they are twiddling so fast that persistence of vision comes into play. Okay. If you are hooking this up to LEDs, you can do some cutesy things. Like you can hook it up to a 7-segment display if you want. And using a single port, you can set the 7-segment display up. Okay? This is an example of how you might display a 1 on a 7-segment display. Remember, 7-segment displays have a bunch of segments of 0, 1, 2, 3, 4, 5, 6 for a total of 7 segments. So in this case, if we wanted to turn on segment 1 and 2, we turn on bits 1 and bits 2. All totaled, the code would be pretty simple. Here we loaded up R20 with a 6 because that's the hexadecimal value of that number. We sent that out to port C, and we turned all of the bits on. Again, this is not how I would have done it. I would have swapped it out, DDR-C first. The school of thought there is let's have known stable values on the port before we set it as an output. So it happens to be how I do it because of what I'm usually interfacing with. I'm usually interfacing with other high impedance inputs, so it doesn't matter.
Is there a reason why it's at the very end it goes L1, R jump L1?
Right, so the reason it does this, R jump L1 says go to L1. Well, that's the same line. So in one of the other examples, I just put a comment there. That means halt. Just stay there. Just, okay, it's going to go to L1. Oh, you want me to go to L1? It's like those comics you see online. To keep insert whoever you want to insult busy, give them this card, flip over. To keep whoever you want busy, flip over this card. You know? And so you do that over and over again. And you basically apply that to whoever you want to insult on the internet. Which, you know, let's all try to be nice to each other on the internet. Here's an example of a 3. Somebody tell me, take a moment, tell me what hexadecimal value I need to store into the port register, specifically port C, in order to get a 3 to appear. Remember, the bit positions are labeled 0, 1, 2, 3, 4, 5, 6. If the segment is lit, you need to put a 1. If the segment isn't lit, you put a 0. So somebody tell me what number I need. Give everybody a second. Yes? 4F. I like 4F. What do we have to put in the data direction register? FF. They all have to be outputs because we do have to output a 0. Okay? But only 4F will go on the port register. There you go, 4F, FF. Thus far, we've only talked about output. And output is what we do most of the time. But input is equally important, and there's a whole bunch of hardware to do with input. So when we're dealing with DDR equal to 0, there's a few things we need to consider. First off, this is a full program that does both input and output. We start by putting a 0 into DDR-C. That makes all 8 pins on port C into an input. Now, I say all 8 pins, but I'm actually lying a little bit. Does anybody remember why I'm lying a little bit when I say all 8 pins? Because C only has 7. But for now, we're setting all 8 bits to 0, which means all of the pins of port C are being set to inputs, even though there's only 7 of them. So don't get confused if I accidentally say 8 bits. This code, by the way, you can tell is written for the Mega 32, which does have 8 bits on port C. The code is almost word for word compatible with the 328P, with only a few notable exceptions. Okay, so the concepts are all the same. The syntax is ever so slightly different. So putting a 0 into DDR-C makes all of C into an input. Then we reload R16 because we're done using R16 as a 0, and we make all of port B an output. Okay. Then we've got a loop. We can see we're going to be running this set of code over and over and over again. In, LDI, add, out, RJump. In, LDI, add, out, RJump. And this code uses in to read from a register we haven't talked about yet. When we want to get the status of the outside world, we use the pin register. It's one of those 3 registers I talked about: DDR, port, and pin. Pin is just for input. If we want to know what's happening on the outside world, we use the pin register. So we read in from the pin register, and that tells us what is on those 8 pins or 7 pins of port C. Then what do? We load in 5 to R17, and we add 5 to whatever that number is. Okay, so here we've loaded in, let's for now say 8 bits of port C. We've added 5 to it, and then we sent that number, R16, back out to port B. So what this effectively does is reads in a number from the port C, adds 5 to it, sends that sum to port B, and it repeats that forever. So if I were to hook up switches to port C, 8 switches to port C, and 8 LEDs to port B, whatever I had on my switches, that plus 5 would appear on my LEDs. Now, this is still running at 16 megahertz, so it's still going to be updating that 16 million times a second, well, minus the time it takes to run this, okay? But the switches stay constant, so the sum will remain constant. So overall, the LEDs will appear to be constant, even though we're updating it several million times a second. Okay. Now this uses inputs that are high impedance. So whatever switch I need to use has to provide both a high and a low. If I only have a switch like I showed in the reset circuit that connects directly to ground, I've got to use this internal pull-up resistor, and that's what I want to spend a little bit of time talking about now. So this is an indicator of the flip-flop in the pin register. There are 8 pins, 8 flip-flops in the register, labeled pin A0, pin A2, pin A3, so on and so forth. Now there is a magical switch in big quote marks, that will open and close depending on what you put in the port register. Now I said port is for outputting. Port is for outputting, but if we are using that pin as an input, and when I say pin, I mean physical piece of metal, we're using that particular pin as an input, then the port register really doesn't serve any purpose. So we use it to indicate whether this magical switch should be open or closed. If it's a 0, that switch is open, which means no current will ever flow in either direction through that pull-up resistor. If it's 1, that pull-up resistor switch is going to be closed, and so current will flow out of this or into this as necessary. This is sort of the outside of the chip right here. On the left is outside, this is inside. So these pull-up resistors reside inside of this. So I want to go over, there's like 5 different combinations we can have, all right? First is if the data direction register is 0 and the port register is a 0. That's our first combination. We just have a high impedance input. If the data direction register is 0 and the port register is 1, that implies an input with a pull-up resistor. Okay. If we have DDR as 1 and port is a 0, that outputs 0 volts. If we have data direction register as 1 and the port register is a 1, that outputs 5 volts. One more combination that I haven't talked about yet. If the data direction register is 1, which means if the data direction is 1, is it an input or an output? Don't all speak up at once. Output. If it's an output, the pin register is basically useless, right? Because we're not going to read in from an output. That would be silly. We can, but it's silly. So just like when we're using the pin as an input, the port register is useless, so we use it for some other function. When we're an output, we use the pin register for an extra little thing. If we put a 1 in the data direction register, and we write a 1 to the pin register, it will toggle the pin. So whenever you see the word toggle, think of that. If you want to toggle a pin, you write a 1 to the data direction register, means it's an output. You write a 1 to the pin register, whatever the current output on this pin is, will swap. So those are the 5 cases of I/O setups. Now, overall, there's a lot of hardware going on inside of this chip. Each port pin has the following setup. They've got these 2 registers that deal with the output. They've got a register that deals with the input. Now, the physical connections to the outside world go to both. They go to both the output section and the input section at the same time. Inside of each of these, there's more hardware. And it's stuff that you should be familiar with from 260, from Digital Logic. Here it is again. I have colorized it. This is the output section. That's the input section. First thing I want to call attention to right in the center, that symbol. Remember what that is from Digital Logic? Inverter would have a bubble on it. It's a type of buffer. It's a tri-state buffer. Tri-state buffer basically turns this into a magical switch, right? If we are enabled, this will act as just a wire. If we're disabled, put a 0 here, this acts as an open. It will not be connected. Now that makes a lot of sense if you look at where that enable comes from. It comes from a flip-flop labeled DDR. Right? So if you're playing Dance Dance Revolution, you have an output. Some of you chuckle. A for the day. So this is a representation of 1 bit in the data direction register. This is 1 bit in the port register. And over here, this is 1 bit in the pin register. I'll get to this synchronizer shenanigans in a second. So if we are disabled, then the value on the port pin doesn't matter because it will never make it to the physical pin. The only route we will have is through this input section. Unless this thing, this is a MOSFET or some kind of a FET. I don't know exactly how it's implemented, but for now we'll just call it a FET. If you put a 1 here, we'll be connected to 5 volts. If you put a 0, it'll be an open. So let's follow that back for a second. Goes through an inverter, goes through this magical AND gate. Now these 2 signals are control signals from elsewhere. Specifically, we care about if the data direction pin is 0. If the data direction pin is 0, what kind of a mode are we in? We're in an input. So if we are in an input and the port pin is 1, which is exactly what we said before. If we are an input and the pin is a 1, we're going to activate this pull-up resistor. Okay, and that inverter is there to make sure that the I/O logic works just fine. This final piece, you may be asking, what's that? That just stands for pull-up disable. It's a feature inside the processor that, unless you specifically go looking for it, will be disabled by default. Okay, or rather, it will be pull-ups will not be disabled. So PUD pull-up disable is always inactive. It's one of those double negative things, right? I don't know if I just said it correctly. Assume that it doesn't exist in this diagram. Okay, so the only 2 things you really need to worry about are the DDR needs to be 0 and the port pin needs to be 1. But because the DDR is 0, that 1 on this port register doesn't make its way to the physical pin. Okay, the rest of this is the input section. Here's what happens. Comes in. This is a, just think of it as a tri-state buffer for now. I don't want to go too deep into this. Basically, if we're asleep, which we haven't talked about what a sleep mode is, but this processor can go into low power sleep modes. To save power, it'll basically turn off all this circuitry. So this is the gate right here that says don't let anything in or out. It then goes through a synchronizer, which adds a single clock cycle delay. You can see the clocks are connected to a single clock line, just like we had in our shift registers, and that's what this is. It's a shift register, a 2-bit shift register, to prevent things like glitches and spikes and so forth. and that goes off to the bus. So when we read things, we're reading from this register, which is one clock cycle behind everything else. This is the basic setup. We got a DDR register, a port register, and a pin register, and that's how they all work together to form those 5 states I just talked about. Well, not really. Talks about 4 of those states. To get that 5th state, that toggle state, we have to go right to the data sheet for the 328P. This is sort of a generalized diagram for all AVR cores. The 328P has a special piece of hardware. Let's play Spot the Difference, right? In our Highlights magazine, Spot the Difference. There's one. There's the other. And apparently I wanted that highlight thing to come on after I got a chance to ask you this. But here's the difference, okay? We've added in a multiplexer and an inverter, okay? That inverter is responsible for toggling. The multiplexer is responsible for dealing with the inversion. You've got to follow this along here, but this multiplexer's select signal comes from this gate that says WPX. WPX, if you read the data sheet, is a write to a pin register. So if you write to the pin register, it swaps. Normally it goes right from the data bus to that port pin. But if you write to the pin register, it gets it from the inverse of the pin. So this is almost like a T flip-flop kind of a setup. In fact, it's very similar to a T flip-flop. Okay. Everything else is the same. Got that, and this shows a little bit better. That MOSFET has a little bubble on the input, so it's active low. This is an AND gate, so we invert it to make it. We invert it to make everything work out okay. Does it still work okay? Nope. Okay. So we have this option to invert, which is super important. Now that we have all this hardware, let's go through and see how this works when we are outputting different things or inputting from different things. So let's for a moment assume that we have put a 0 on the data bus for this port register. Currently, the data direction register has a 1 in it. Data direction register being 1 means that this is an input or an output. It's an output. Laser pointer. So here's the pin, here's the, where did you go? Oh, I have to be clicking. There's the data direction register, right there. Or maybe what's going on? All right, that'll work. So we've got, now I have no screen. But I do have the laser pointer back. Okay. Oh, just get out of there. Just go away. Okay. So, when we're outputting something, it goes through the port register and hits this tri-state buffer. The tri-state buffer is enabled because of the data direction register, which allows that 0 to go all the way out to the pin. When we're outputting a 1, same stuff happens. Because the data direction register is a 1, that tri-state buffer is enabled. So the data comes out of the port register, through the tri-state buffer, and out to the pin. Interestingly, note that because we're driving this, we could actually read in from the pin register and see what the output is. It's something we could do. So let's say that just for fun, someone decided to be bad and hook this directly to ground. They physically tied this pin to ground. What happens when you try to drive 5 volts to ground with nothing, with just a wire? Badness happens, right? If we use our Ohm's law, V equals IR, I equals V over R. V is 5 volts. R approaches 0. And when you take 5 divided by something approaching 0, you get an answer that is approaching infinity amps, which sounds like fun. So what would be happening, though? We would be seeing something bad happening here in all likelihood. Okay. So one more oh, my slides are all messed up. This was supposed to be for you. write a program that continuously sends out to port C 55 and AA. We've actually already done this one. The only thing we have to make sure we do is set up DDR-C to be all outputs, and then in a loop. All right, so you've already learned a little bit about this loop instruction. We write out 55 to port C, and then we write out AA to port C. I'm glossing over each of the individual instructions that make this happen, because I'm hoping by doing that you will get used to seeing them. Outputting to an I/O register involves loading in an immediate value into a register, and then using the out instruction to put that data that's in the register into the I/O address. Okay. Let's also look at input sections now. So now, on the data direction register, we've got a 0. Whatever is on the port register comes up to this here. Whatever it is. So, by the way, this little arrow represents how the contents are going from port to the pull-up resistor. So it flies through here, activates this pull-up resistor. Or doesn't, depending on what its value is. There's no value there right now. Meanwhile, because the data direction register is 0, whatever's coming out of this port register doesn't matter because it's completely cut off. The only way for things to happen, data flows into the pin through this synchronizer and onto the data bus. Off camera, off this data bus, that's everything else in the processor. There's tons of other stuff in there. But for the moment, all we care about is these 3 registers. This synchronizer runs on the I/O clock, 16 megahertz or 20 megahertz, whatever you're running the processor at, and is there mostly to deal with glitches. The one thing that you have to be concerned about occasionally is if you write to a port and then try to read in from a port at one instruction after it, you're going to get the value that was on that pin 1 cycle ago because of this shift register, this 2-bit shift register. So if I outputted a 1 and then read immediately from that same bit, I would not see that 1. Okay? I would have to wait 1 more cycle. All right. Your turn. Write a program that reads all 8 bits from port A and writes to all bits of port B. Be sure to set up both port A and port B.
You said
All 8. So figure externally you've got 8 switches on port A and 8 LEDs on port B. Alex,
what kind of read do you want?
what kind of what?
Read would you like? High impedance or low?
Your choice. Do both, since you asked, Alex. Just Alex, though. Everybody else can just choose. Alex has to do both. Somebody left white strips up in the booth.
Just in case. Never know.
I don't ask questions. Okay, let's talk at high level for a second before we get into code. First thing we got to do is set up our 2 ports. Who can tell me whether we set port A to an input or an output? Let's do a raise hand kind of a thing today. Yeah, sure.
Output.
You want to set port A to an output? No. If we're reading from port A, that means that that's an input. Okay, and port B should be the output. So the next question is, how do we do that? What do we have to write to the bits of DDR-A to make it an input?
0.
0. And what do we have to write to the the bits of DDR-B to make it an output? Somebody else? FF, or 1s, yeah. So that's our first step. We got to get 0 into DDR-A, FF into DDR-B. Then, from that point, we've set up our ports. Next, we have to read in from port A and send that data to port B. Now, is there one instruction that will do that? Copy from A to B? Well, not quite. SDS only goes from memory to a register. In only goes from memory to a register. Out, memory to register. Well, in opposite directions, right? So it's going to be a 2-step process. First, we've got to get data from port A into the CPU, into some register. Then we have to send it back out to a different I/O register. So here's a solution. Not the only solution. First, 0 into DDR-A. 2 lines that do that. Next 2 lines, FF into DDR-B. Each time they're using a temporary register, R20, to do that. Here's my loop. In from pin A, and this is the other trap. You've got to read from pin A, and you have to write to port B. Pin for read, port for write. If you read from port, that's not really what you want it to do. It'll kind of work because of, it'll work in that it'll tell you what you wrote to it the last time, but not what is currently on the pins, okay? So read from pin A, output to port B. Okay. At the beginning of class, I promised that by the end of this, you were going to understand how to read and write to I/O pins. Describe the underlying hardware of the I/O pins. The underlying hardware of the I/O pins, by the way, is just a register, a flip-flop, okay? Name the ports on the 328P. Quiz. What ports are on the 328P? By a show of hands. Somebody. Oh. 1, just 1. Yes. No. That's not on the 328P. Port B.
C.
Port C.
D.
Port D. You were so close. Just 1 off. Okay, redeem yourself. What processor does have a port A? What are you going to do? There's no danger of being wrong here. I mean, there's a fine chance you're going to be wrong, but there's not a penalty for being wrong. The 28P is not an Atmel processor. Good try. The 32, and really, if you wanted to expand it to be general, like chips with more pins have a port A. Okay. Know where the button and LED are located. Just as a reminder, where are they located? Button's connected to B7. The LED is connected to B5. So you probably almost always want to make B5 an output and B7 an input. By the way, this button does not connect it to both 5 volts and ground. It connects it only to ground. If it only connects it to ground, that means you must use a pull-up resistor in order to make it work. B5 and B7. Okay, the things I have not done yet. Adjust a single I/O bit without affecting any others. Thus far, when we write to DDR-B or to port B or to pin, well, read from pin B or write to pin B, right? Why would we write to pin B if it's an input register? Why would we? No, we don't toggle high impedance and pull-up. That's writing to the port register. We do toggle the actual output. If you're set up as an output and you write to the pin register, that toggles from a 0 to a 1. Okay. But that affects all of them at once. We have to write 8 bits at a time. So let's skedaddle on to I/O bit manipulation. Yes?
I just wanted to check my understanding for the example question we just did.
This one?
Yeah. So we set the DDR-A and DDR-B
Yep.
to 0 and 1 just to initialize it.
Yeah, so they're registers, so they hold their values as long as they have power. So by setting the first one to 0, that sets all 8 bits of port A to be inputs. Okay. If we had put 5 in there, half of them would have been inputs, half of them would have been outputs. Okay. So this is all 8 of them are inputs. All 8 of the bits of port B are outputs.
Why would we set all of them?
Because that's what the program asked us to do. That's what the problem statement said.
Okay.
I said, assume that there are 8 switches connected to port A and 8 LEDs connected to port B. Yeah.
So, my mom has this.
I can't even.
Sorry. So, it's like this black box that has 2 CD lines.
I'm mature. Your mom has a black box.
Black CD in one, and black CD in the second one, right?
Yes.
And then it copies and pastes whatever's on that CD.
Yes. Okay.
Is that what's
It's. I mean, there's a lot more going on there because it's an optical medium, so it's spinning, but it's effectively reading and then sending out to the next one. Yes.
So it's using a processor similar to this?
No, I would say that that's not a good bet. There's a lot of decoding that's going on, but what it's effectively, it's not quite doing, well, it's more like that example we did last class where we did an LDS and then an STS, and then an LDS and an STS. Over, and it's loading from a memory location and storing to another memory location. Yeah, it's they're doing, but well, I'm not sure exactly how the optical works out. They must be doing it a bit at a time because it's rotating, but the reads a byte at a time and then writes out a bit. Well, something like that. At some point, yeah, there is a laser turning on and off. So probably it is pretty similar to this. I thought those were illegal though. All right. I'm going to need a couple of movies from your mom. All right. She can, we'll talk after class. No piracy. I/O bit manipulation. Okay, so there are some special instructions. We're going back into learning new assembly instructions mode after that brief detour to Alex's mom. These instructions, I'm going to pull it together, guys, I promise, allow you to manipulate a single bit, not a whole byte at a time, but a single bit inside of an I/O register. This only applies to I/O registers. Here's the first one, SBI. I get to do my favorite joke. Not on this slide, though. Set bit in I/O register, SBI, set bit in I/O. It follows the same pattern that all assembly instructions follow in that data flows from right to left. Eventually, I will get you all responding in unison like kindergartners, yeah. But the difference here is this I/O register, whatever you said, doesn't get set to this value. When I say SBI port D0, that doesn't set port D to be 0. It actually is always going to set something to a 1. SBI for set is a 1. It's going to set, and this is sort of pseudo code. It's not real code. It's not C code. Port D pin 0 or bit 0 is going to be set to 1 without affecting any of the other bits. Setting DDR-C bit 5 to be a 1. And here's its actual opcode. It uses the first 8 bits to indicate that it's an SBI. Then there are 5 bits for port A and 3 bits for port B. So how many different bits can we set if B is for the bits? Three bits means what's the maximum number you can represent? 7. 8 total bits. And that's convenient because we have an 8-bit processor. So we can set 0, 1, 2, 3, 4, 5, 6, 7. Any of those bits, we can adjust a single bit. And there is a complement to the set bit in IO register. It's the Thomas Jane instruction. CBI. No? Nothing? Jane? Snarky? Blonde hair? Great smile? Thank you. CBI, California Bureau of Investigation. If you go back and look at last year's lecture, you'll see I tried just as hard. So I want you to know that this is an ongoing struggle for me. Anyway, it's the same pinout for A and B. 5 bits of A, 3 bits of B, but you'll notice there is a single difference. Somebody tell me what's the difference between these two instructions. Yeah. I've been specifically about the opcode. So that's the two of them going back and forth. Yep. Opcode. There's a 1-bit difference in the opcode right there. Whoop, too far. That is a 1 when you're doing an SBI, and that is a 0 when you're doing a CBI. That's the only difference. But it does the same job, except instead of setting something to 1, it clears it to 0. Okay. Now, there are some limitations on these two instructions. They don't just work anywhere in I/O space. They actually only work for part of the I/O space. And that's where this table comes in. They only work for the first part of the I/O space. Specifically, actually, they don't even work that far. 5 bits, 2 to the 5 is 32, I think. Works for the first 32, which I think gets us up there. 20 to 30, 0 to 20. No, it stops right about there. Right about the EEPROM. Okay? So it only works for that. But the important thing is all of our I/O bits are there. And also some things to do with the timer and the EEPROM. A few other cutesy things. Okay? But all of our I/O stuff is in there. So when we're trying to twiddle bits for the I/O pins, we can use the SBI and the CBI instructions. Okay. IO 3B are simple, just groups of bit sreg at top. So pointing out, I wanted to point out that all of this at the bottom, that's your IO stuff. Up at the top, you've got things like the status register and the stack pointer. Everything in the middle has something to do with some peripheral inside the microcontroller. All right, but these two, that's the status register and that's the stack pointer that are all inside the CPU. Okay, your turn. Let's use these instructions. Hi-ya. Write a program that will toggle port A, pin 4, continuously. I'm not giving you any hints. There are a few things that you need to do. And the goal is to not affect anything else in any register, just that bit. And I suppose if I really want to limit you, try to do it without using LDI. Try to do it without using LDI. All right. So at the high level, there's really only two things you need to do. First, you need to make sure that DDRA bit 4 is a 1. So you need to write that bit. And then you can just go back and forth setting that bit and clearing that bit. Now, I said try to do it without LDI. It would have been easy enough to do an LDI with a 1 in the 4th bit position and do an out. But that's 2 instructions. And when we're going down to the trouble of doing assembly instructions, it's about speed and it's about code size. So if we're only trying to deal with port pin A4, we're not going to we're going to be in the right thing. We're not going to bother doing an LDI and an out. We can do it in one step. Here, I've SBI'd DDRA, 4. That turns just that pin into an output without affecting the other pins. Okay. If I had done LDI, I run a big risk. If I had done it with LDI, I would have said something like the 4th bit position, 0, 1, 2, 3, 4. I would have loaded 32 decimal or 10 hex, right? I would have loaded 10 hex into a register, say R20, and then I would have stored R20 into DDRA with an out instruction. There's a problem with that, though. What if before this code ran, all of the other pins on port A were declared as outputs as well? So what if DDRA had FF in it? In my attempt to turn that one pin into an output, I've now turned all the others into inputs. This is something that'll happen when you start copying, pasting code around in large files. Right? If you don't know what the status is of those other pins, or what they should be, you want to leave them alone whenever possible. So here, this is the better way of affecting just that bit, because the only way you could have done it, you would have to do an in, then you would have had to do some bit masking to mask that bit to a 1, and then you would have had to do an out. So it actually ends up being like 4 instructions instead of just 1 instruction. Alex?
Can you SBI more than one pin in one line?
No. Nope. It's AVR architecture. It's dumb. It does one thing. If you wanted to set 2 bits, you'd have to use 2 SBI instructions. If you wanted to set 8 bits, you'd have to use 8 SBI instructions. At some point, there's a trade-off between the number of SBIs and the LDI and so forth. I think it's around 4 or 5 bits. Okay. But depending on how you're doing it, it may be easier to maintain even with 8 SBIs. Here's my loop: SBI, CBI, RJump. Now, I can do this in 1 instruction instead of 2 instructions. For a gold star for the day, who can tell me how to toggle a pin forever without using 2 instructions here?
Set the output on that pin to 1.
Give me the full instruction. So I'm not sure. You might be right, but what would the actual instruction be? Instead of SBI port A4, CBI port A4.
SBI A4.
Yes, that is absolutely right. Gold star for the day. What's your name, by the way? Set. So this will set and then clear and then loop. If you instead use that special mode of toggle, you can just say SBI pin A, 4. Don't clear anything. If you set that bit repeatedly, it will actually toggle repeatedly. All right. We're about done, right? Okay. We've labbed today, this afternoon. Okay. You are expected to have the lab handout, right? We're doing lab 1 flags in lab today.